Welcome to our latest webinar in this series. I can see some people are still filtering in, so kind of to get a slow start here. But I'll go ahead and introduce the webinar while people are filtering in. So my name is Megan Dahlhauser. I'm an editor with PRX Quantum with APS. And this is a webinar entitled Sensing the Quantum World, Quantum Optics and the Nature of Light. So a little bit about this seminar series. The American Physical Society, in partnership with the Johns Hopkins Science Diplomacy Hub, welcomes you to an innovative international event dedicated to advancing global collaboration and understanding in quantum science and technology. This is one of several worldwide initiatives to celebrate 2025 as the International Year of Quantum Science and Technology. Our experience helps connect scientific communities, industry leaders, policymakers, national labs, and the public, fostering discussions on the transformative impact of quantum technologies. All the previous webinars from this series can be found on the APS YouTube channel, and this one is also being recorded and will be posted there later. Today, we have our 7th installment in the Quantum Connect webinar, and today we are joined by Philip Chrostoski and Animesh Datta, sorry. And we may have a third speaker as well who may or may not be able to join us for a portion of the discussion as well. So to get started here, we'll have our panelists introduce themselves and tell us a little bit about what they do in the quantum industry, particularly with regards to our topic today, which is quantum optics and the nature of light. So whichever would like to get started, feel free to jump in, especially as we go through all of the questions as well.
Okay, I guess I'll go ahead. Right, so I'm Animesh Datta. I'm a professor of physics at the University of Warwick in the UK. To a brief background, so I did my undergraduate in electrical engineering from Indian Institute of Technology in Kanpur. There I got interested in quantum things, so I did a PhD with Professor Carl Caves at the University of New Mexico in the USA, which involved both quantum sensing, some of quantum optics, and also quantum computing. Then I came to the UK to do a postdoc with Martin Plenio at Imperial College, and then another postdoc with Professor Ian Walmsley at Oxford, which was an experimental group. And then I started my own group at Warwick about 10 years ago, and we work on quantum sensing, quantum computing, and other related things. Thank you.
Thank you. Thank you for joining us today.
Right. So, yeah, I'm Philip Chrostoski. I am currently finishing my first semester as a professor of physics at Waldorf University in Iowa. I just recently finished a 3.5-year postdoc at Sandia National Laboratories. I do theoretical and computational quantum information, specializing in looking into non-idealities and quantum sensing applications. So, yeah, I stumbled to where I am, started undergrad doing nonlinear optics experiments, and then eventually in grad school, I moved into quantum information theory. So that's me. I'm the young one here.
Well, thank you for joining us. It's good to have a diverse set of backgrounds and experiences so that we can have a really informative discussion. So our first question for you both is, what was your kind of first quantum moment? So kind of the experience that first sparked your personal interest in quantum technologies and set you on your current career path.
Or maybe Philip can go this time.
Yeah, okay. Yeah, I was actually just recently thinking about this. So, as I just mentioned, coming out of undergrad, I actually was doing like experimental optics. I thought I'd go on to work at NVIDIA, because at the time they were doing a lot of augmented reality stuff. I was like, oh, that's cool. I was working in like a nano fabrication lab my first year of grad school, and I found out that experiment, especially in that area, I did not enjoy. So I was, I really enjoyed my quantum mechanics classes in undergrad, and then going into grad school, I was, I found, the graduate level stuff just so interesting. I eventually talked with that professor. She had an opening in her research group, and I was like, I don't think I'm much of a theorist, but I'll try and switch over, because she was working in quantum sensors, and I saw it and I'm like, okay, so these things will essentially replace the thing I'm working on in my lab. Why am I working on this? This is so much more interesting, because you talk about ultra sensitivity and things they can do just even at the time, this was only about 10, 11 years ago now, was just unmatched to anything I had seen before. And I had to kind of dive in and learn more about it. And quantum is so counterintuitive that you just kind of fall in love with trying to figure out the problem that's going on. So that was my moment, just kind of seeing how this technology could really bring in the next revolution.
Yeah, so for me, I think well, I'm the old one, so this was 25 years ago when I was sort of in second year of undergrad. And as I said, so I was an electrical engineering student, and in the department, there was a seminar speaker who had been invited to sort of give one of these seminars in the department, and it was about quantum error correction. I knew nothing about quantum. I mean, I knew a bit about quantum physics because I had done like an undergrad course in the first year, and I knew a bit of physics, and I liked physics. And then this professor, K.R. Parthasarathy, who's passed on now, he talked about how you only need 5 qubits to correct all errors in all single qubit errors in a quantum system. And that was the moment that I thought, oh, this sounds very interesting, although I don't understand what a qubit is or what an error correcting code is. I thought that this would be a very interesting thing or worthwhile thing to study that brings together my interest both in quantum physics or physics more generally and electrical engineering. So then I set about sort of trying to learn the little ingredients piece by piece. I got hold of the book by Nielsen and Chuang, which is sort of the standard textbook in the field now. Back then, I think it had just been published. So this is 25 years ago, I think in 2000. I don't think even the library had a copy, so we had to like order it for the first time. But then I started studying, and then I did a project, and I joined for my PhD, and then it went on from there. But yeah, very interesting, at least for me personally.
Yeah. So both of you kind of talked a little bit about like how, it sparked your interest while you were kind of currently studying something different. So my next question for you is, what are the challenges or obstacles that you faced when making that transition into like quantum computing work and research? And do you have any advice that you would give to students or professionals that are looking to make a similar shift?
Okay, maybe I'll go this time. I mean, okay, so this depends, I think, much on what specifically one wants to do, because the field is now so vast. I think it's impossible to give any advice that applies to a substantial fraction of the people. So I think we are a bit hamstrung on this panel because I think we are both theorists. And although I've been in experimental groups, I've never done experiments myself. So just from my own little sort of experience and let's say activities on the theory side, I think learning as much basic maths and physics as you can at the undergraduate and the graduate level, I think is very important. I know it's very tempting to get attracted by the notion that somehow quantum sensing or quantum computing or quantum technologies are very exotic and nobody understands them and so on and so forth. I think that's not quite correct. They are based on fairly standard undergraduate curricula. So if someone is a good student of physics and mathematics, I would think they would have no problem in doing very well in quantum information science and technology. I think that's at least my understanding. And also, having been a professor for 10 years now, I can see that happen as well. Like, students who are good in physics and maths are perfectly well equipped to do well in quantum information science.
Yeah, I think I really have to agree on this. I think the only advice that I can give is just have a willingness to learn. And that's kind of what all science students going to science kind of already have that. Like, they want to understand how things work, so they're going to learn how they work. I had I helped mentor a summer intern while I was at Sandia. It turned into a full year thing, and he started working in open quantum systems. He had just finished his first year of undergrad physics, and he's going into something that you could say is really complex, but he had a willingness to just learn on his own. The internship is about teaching them, and he did a really great job in just learning, and that's kind of kickstarted him into doing very well. And yeah, a lot of I've been doing theory in this for so long, but I think if you have a good background in math and physics, you can really just hop in anywhere. My little ragtag group, and it's not my group, I was part of this group at Sandia, were made up of people looking into atom interferometry that are coming from different areas. My background's in quantum defects, really condensed matter type of stuff. The person I was working with spent years doing more of, he's got the atomic side done very well, and the optics, and it's kind of us all just bringing our skill sets together. So if you have that good fundamental base, you kind of ready yourself to do well in the field in general, because at its heart, it is just that a lot of what we do is the same thing. Like, I apply the Schrodinger equation to a Hamiltonian all of the time, and you learn that in your undergraduate quantum courses. So once you have that good base, you're kind of just setting yourself up for success if you're interested and want to put in the time to learn, which at that point, if you've gone that far, you're already on your way there. So
So how has the landscape of quantum technology in optics and light evolved since you began your career? And are there any developments that have surprised you a lot as you've kind of seen the field change?
Philip, do you want to go this time?
Sure. So reading over this one's a little hard for me. I've been in the field. I'm still considering myself an amateur. And there's so much of the field I don't know. I joined Sandia learning about a topic I'd never heard of before. So I think how things have changed, it's more of kind of the things that are popping up that we still don't have, like, maybe a clear understanding about. So, you know, uh, in people have been working in atom interferometry for 20 years or so, but it's still a topic where we're still trying to learn all the nuances about it. And as you dive deeper into it, you kind of see where maybe areas that you didn't think would actually affect what's going on are. So I think how it's changed is that, to me, it's more that, like, it's just broadened so widely. You have so many different areas kind of tackling the same problems now that you have to think about them a lot differently. I can't just think about them in terms of, like, a physics mindset. Maybe I need to think about it in terms of chemistry or biology, because that's where these technologies are going towards. So I have to start learning about this. Otherwise, I'm just not going to be able to, help out and try to, understand these things that are popping up. So I think that's how it's changed the most in the short time I've been in the field, is just see kind of this narrow mindset I kind of had coming out of undergrad into graduate school really widen up into that I need to start thinking about things in areas I thought, I took Gen Chem and I was like, I'm never going to need to really think about this. And I was very wrong. So.
Yes, I'm just reading the question again. She said quantum technology in optics and light. I mean, okay, so begin a career. I mean, as I said, I mean, I got interested in this field more broadly since sort of like as an undergrad in about year 2000. And then during my PhD, which I started in 2003, I was sort of working on theoretical topics, such as quantum optics and so on. And back then, it was still thought, I think, certainly I thought, and I think other people also probably more senior than me thought that the theoretical ideas were, let's say, more advanced than what the experiments could achieve and implement. That has certainly changed in the last 20 years. And then my personal view is that we are at a point where the experiments or the technology can do things that theory hasn't yet come up with, right? And certainly true in quantum computing, right? I mean, we still have the same basic set of quantum algorithms we had back in like 2000, right? We have the phase estimation algorithm and the search algorithm and the Fourier transform, and it's basically still that, right? So, and the same is true, I think, in sensing. I mean, we still basically have things like squeeze light and single photons and so on, but the technology has now advanced so rapidly in the last 10, 15 years, I would say. I mean, all the areas related to quantum technology, but certainly in optics and in light, right? I mean, of course, it's not as advanced as we would like it to be, but I think the potential to implement things, that surprises me the most, right? The kind of things. I mean, in optics, obviously, the perennial problem in optics, which is photon loss, is still there, and it has not yet been overcome. But beyond that, I would say there's a lot of advance on the technological side, and not just in quantum optics, right? Even in classical optics, nano-optics, nanophotonics, these kinds of things, these fields have advanced extremely rapidly in the last 10, 15 years.
And I'm just going to jump on that. I think anymore, like I find myself looking at experimental papers and talking to experimentalists to kind of gauge how I'm trying to think about a problem more often, because they kind of have that great intuition, because they have all of these new insights they're doing so much more rapidly than I think some theory and computation is doing. So my group, we're constantly in touch with experimentalists in the field to kind of see where we need to go. They're kind of, it's kind of been this flip, at least from my point of view, that kind of they're leading the way a bit more. They're making more advancements, so we're trying to help out where we can on the theory side, but they're, they have the reins at the moment.
That's a really great insight. Yeah, I think that connects to the next question that I have for you too, is also that as the field has continued to progress, Animesh, you briefly mentioned some of these algorithms that we still have maybe not as much progress as we'd like to see. What quantum optics application areas do you believe might deliver the first commercially significant breakthroughs? And if there are any you can pinpoint, why do you think so?
Well, I mean, commercially significant, I mean, certainly in the area of sensing, right? I mean, light is in some sense the sensor par excellence, right? I mean, it can go very far, it can go very quickly, it can go through many things. I mean, not all things, but for many things. So I think in that sense, there is, I would say, I mean, optical sensors are a huge field in among themselves within sort of engineering more broadly, and not quantum optical sensing, just optical sensors, right? I guess then in the quantum domain, I guess, I mean, well, it depends also a bit sort of how you semantically define these things, right? So there's a lot of interesting and very promising, maybe even commercially viable applications of things like nitrogen vacancy centers and things like that. I mean, they're not technically quantum optics, but you read them out optically. So in some sense, there's an optical interface with these things, and they then make a very effective sensor for all kinds of applications, right? I mean, there are proposals, or even I think actual companies selling or trying to sell quantum sensors or NV-centered sensors in biological applications. There are these optical magnetometers which can scan brain waves and all kinds of things. Yeah, I can't. I mean, there are many more, so I don't know, but maybe I should give Philip a chance to sort of mention some of his from his side of things. I mean, atom interferometers, the kinds of things he talked about, they are a very big. I'm not. Maybe he can comment on the commercial side of those things, which I don't know very much about.
Yeah, so atom interferometry, which I've only actually been working in that for about 4 years. I am more on the side of like NV centers and other defects. So I was gonna kind of bring those up, but those are more of like a material thing. Like, you do have like an optical readout, but it's more that, they're kind of it's more material over optics, and they're just using kind of optical things we've used classically for a while in them. They're just, you're controlling a spin in there to do some optical readout at the end. Atom interferometry, there are, some commercial gravimeters out there, and inertial sensors. I will say, like, commercial, it's not like everyone can get their hands on these things. And that will be big. And so, like, I'm kind of twofold if we're talking about like what's going to be big in the next few years, in terms of commercial. I think, atom interferometers, because there are ways to make them smaller. Like, if you Google what atom interferometry right now, the big thing happening is like the MAGIS 100 project up at Fermilab. But that's a 100-meter tower. I don't think anybody can just dig a 100-meter tower for themselves. That's kind of hard. But there are ways to use atom interferometry very compact and make these inertial sensors, which would be good for GPS and other things like that, and really advance that area. And then defect sensing has, really come a long way. There are people looking with NV centers at, doing stuff at room temperature that we can do for biology, and in other areas. But there's, still a lot of noise in those systems. And so once those can get figured out, we're already seeing that we can have long coherence times of which allows us to do these readouts very sensitively. All right. At room temperature. It's kind of, we're at this wall, but we're almost there. But then there are also other defects that are showing more promise that might even be better. So it might be that we need to change the material and look at a different thing. But in the end, it's still all a defect in a material that's doing the same thing. So we have all that baseline. It's just now we're at a point of just pinpointing what the best thing will be to really make these commercially viable.
I guess just to sort of comment a bit more, I mean, we haven't mentioned, there's of course, how much of your sensor is only optics. Light just by itself actually doesn't do much, right? Where light doesn't interact with itself, it interacts with other things which are then sort of probing. So we didn't mention clocks. Clocks are a very big part of the technological, commercial as well as sort of fundamental scientific interests. The more sort of, let's say, conventional optical sensing technologies, many people have worked on these for hundreds of years. So things like microscopes, microscopy, spectroscopy. So these are more conventional sensing techniques. And then looking at quantum versions of these things. We work in our group on some of these things. So I think those are I would say, going ahead, probably the kind of topics we would want to look into at greater depth, because these things have a very long track record of utility in the sciences and engineering and commerce, right? I mean, a huge amount of analytical science is just spectroscopy, right? I mean, all the way from chemistry, biology, environmental science, even all kinds of like geology, archaeology, I mean, mining. I mean, a lot of it is just spectroscopy of things, right? So if we can do quantum enhanced spectroscopy, quantum enhanced microscopy, there's like a huge universe of things that we can get into going ahead.
Yeah, these are all such great examples. So tying off of, this kind of topic of where we could find kind of the commercial relevant, applications, the kind of flip side of that is, the discussion about, hype versus reality. So how do you navigate that discussion of, where things are very, hyped and doesn't necessarily connect to where the technology is and where it could believably go, particularly when communicating with stakeholders or investors or with the public? Is that a difficult navigation that you find yourself having to deal with frequently?
Well, me personally, no, because I just say as it is and leave it at that, right? I mean, so we talk to, we talk to people, well, people in the sense of like from undergraduate students, maybe even sometimes like parents of students who've heard about quantum things, all the way to like, I don't know, companies that come to interact with universities or are interested in like funding things and so on. And I think the only way, in my view, is to just tell the truth, right? Because the only sort of antidote to hype, I would say, is integrity, right? Because that is what will survive over time, right? At least in my own personal little view. So I mean, this, I guess you see more in the field of quantum computing than in some of the other fields, maybe not so much in sensing and communications and so on, or other areas of quantum. I mean, you do see sometimes sort of hype in quantum cryptography or something, but it's somehow, well, not somehow, it's for I guess, reasonably good reasons we all understand it, somehow congregates around quantum computing. And there again, I think we just have to tell the way it is, right? I mean, that look, this is what it is, this is what we think it is, and this is what we think is likely, so we can see, or we can have, I don't know, 100 qubits or 200 qubits, but it's unlikely we'll have a million qubits or a billion qubits in the next 6 months, or maybe even the next year, right? So, yeah.
Yeah, I agree. I'm the same way. I'm going to be truthful about at least what my experience tells me is kind of the forecast. The big hype right now is quantum computing, so I tend to leave that to colleagues who work in that field, but I will, try to stay informed by talking with them about it. And I kind of, maybe I'm a little pessimistic. I'll always say it's a little further away because, if it was easy, we'd already have it. So it's obviously hard. So it's going to take time. But I also then add to the end of that is like, I hope I'm wrong, because that means we figured something amazing out, right? So I'll be truthful about what I think, but hey, if I'm wrong, that's great, because it just means we've done something amazing and we've actually lowered that timeline a lot compared to my very pessimistic way of looking at it. But science is hard, so I give a little bit of a pessimistic look at it at times.
So kind of related to that in terms of, other areas that people are very excited about and that are kind of emerging right now. How do you see quantum optics technologies intersecting with some of these other areas that people are really excited about, like synthetic biology or artificial intelligence or advanced materials science, particularly, in the near future? Do you see those intersections happening now? Do you think that those are imminent?
Maybe Philip, you could start on this one.
Yeah, I mean, in terms of biology in those areas, quantum optics and sensing are, that's a big field where they're really coming into trying to, revolutionize ways of looking at things. I know Ronald Walsworth's group, he's now at the University of Maryland, but he showed this while he was at Harvard, is, you would take a little slide of some blood and put it in a normal microscope, and it's just, the noisy black and white image. You put it in near these quantum defect sensors looking for something, and you see this thing light up. Well, that thing that lit up was actually a tumor cell that a normal microscope would not see. So in areas of medicine, this is big. Catching things that are, could lead to something like cancer or something as early as possible is always better. So these are the areas that I think currently looking at, quantum optics or quantum sensors in some way are just going to really kind of push things forwards in how we, treat patients in different ways. But again, it's getting them to that point where they can be commercially available to these hospitals around, the world is going to be hard.
Yes, again, I mean, the intersection of sort of quantum optics with things like material science and so on, I think Philip already said, right? I mean, the interaction of light with these defects and so on. But again, as I was saying earlier, like more generally, I mean, the sort of the fundamental interaction in the universe, like, okay, beyond gravity, that sort of we all live off, is the interaction of light and matter, right? And that's basically what we get with quantum optics. So it has very wide potential applicability. The challenge invariably is that with these quantum states of light, we are almost always dealing with like few photons, right? 1 photon, 2 photons, few photons, and so on. While in a natural application, like people in chemistry or biology who use microscopes or spectroscopy and so on, they use laser light and they can get like billions of photons and so on and so forth. So that gap, in spite of all the sort of impressive advances we talked about a bit earlier, that gap still remains, right? I mean, we don't have a laser for quantum states of light, right? I mean, there's not like a on-demand source of single photons or high photon Fock states, right? So this in some sense is a barrier yet to be overcome. But maybe this is where quantum optics can benefit from intersecting with some of these other fields, right? So like light sources is a question of material science, really, right? What kind of light sources can we produce? Maybe there are techniques in, I don't know, AI or some like related fields which can help in discovering new materials that can produce new light sources and so on. So I think in all of these, it's not always the case that quantum optics helps some other field, but maybe quantum optics benefits from some of these other fields, right? I mean, there's a lot of work in people I know who sort of using molecular systems for quantum light sources. So there's a lot of research in that, right? I mean, there's a lot of research in using molecules to convert light from certain wavelengths to certain other wavelengths, because molecules have a lot of energy levels in various parts of the spectra. So I would say some of these might actually in the end be more interesting if quantum optics benefited from these other fields rather than benefiting them right away.
So our next question kind of ties back to some of the earlier part of our conversation. So Animesh in particular, you mentioned that it's particularly beneficial for, people looking to become the next generation of quantum professionals to have this really nice background in math and physics. Besides these kind of technical expertise skills in quantum physics or algorithms or things like this, what are some other skills that you think are most valuable for the next generation in terms of kind of what the field needs?
Well, some of what I'm going to say is probably too generic, but I think it is important because it's what I tell my students on every occasion I can, which is just the skill, or not even the skill really, the patience to read and write, right? Because we live in this age where we get information in like tiny phrases and sentences, and somehow we try to infer based on that what everything is. It's just not possible. And one of the things you get as a result of this trying to construct the real picture from these little fragments is you get the wrong idea. And that's what hype is. One of the things is the outcome of that, right? You just have incomplete information, but you're trying to reconstruct a much larger whole from these little bits, right? That's also sort of misinformation, disinformation, or just plain misunderstanding, right? Because you can't explain in a sentence or in a paragraph something that is more involved and more sophisticated and more complicated, right? So I think people, if they want to do something worthwhile, must develop the patience and the skill to read and write and just go away and think, really, like not just looking at videos all the time, like, oh, this person said that and that person said this, right? Just, I think in some sense, the more we look at like more advanced things, I think the route to succeeding probably lies in more old-fashioned things. Just go away and read.
Yeah, so that's perfect. And I think it kind of goes back to what I like my advice earlier is just like be willing to learn. Like you can't learn anything by reading a sentence or watching one video. You have to really dive into it and think on your own and ask questions. So yeah, having those skills of just reading and writing deeply a topic is really one of the best things you can do going into any career. And then I would also add with, at least how I see the field of quantum information going is, you need to be able to work with others. You need interpersonal skills too. Because if you can't do it all on your own. I'm cliche, and I will say it again. I wrote it in my dissertation. Is Isaac Newton saying that we all stand on the shoulder of giants. He's not saying he's standing above everyone because he's better. He is saying everyone else around him picks him up. So it's the same way. You got to work with others. So you need those interpersonal skills because it might just be someone else saying something a way they thought about it that clicks something in your head. It's happened to me multiple times where I'm just like, oh, I didn't even think of that. And then, you go on and it kind of breaks you through this wall of getting around a problem. Or it could be as simple as I was during my PhD working, teaching a few courses for my undergrad institution. A professor came in, he looked at an equation, he's like, your units and an exponential don't cancel. And I was like, oh, I redid it. And this code that was getting hung actually came out and finished just because of that. And I was like, wow. So it can be as easy as something as that, but it's, I was okay. I wasn't like, no, don't look at my stuff. I was like, it was open to everyone, and someone else came in and something so simple made me get past this wall. So I'd say my only addition to what Animesh said is you need interpersonal skills too.
Yeah, that's excellent. Very, very true. So we have one more question for our panelists today. For everybody in the audience as well, after we finish these questions, you're welcome to drop in questions to the chat. we have Leo monitoring that. And if we have the ability, we will get to them here. We can also kind of connect you with our panelists as well. But our last question that's, from our planned list here is there any misconception about careers in quantum technology or the field itself that you'd like to clarify for any audience members, especially those considering entering the field?
Well, maybe, yeah. So I would say well, the one perennial misconception is that somehow you have to be exceptionally clever or some unnaturally smart to understand what quantum mechanics is, right? I mean, I think quantum physicists are to blame for this, saying, "Oh, nobody understands quantum mechanics," and so on. And I mean, here in Warwick, at some point, we had a professor sort of teaching second year quantum mechanics, and he had this, like on the web page of the course, he had this picture of Feynman saying, "Oh, nobody understands quantum mechanics." And I said, don't tell that to the first year students who are trying to here to learn. Don't say that Feynman said nobody understands quantum mechanics, because they are terrified as it is. And then you say, "Oh, nobody understands," and their mind sort of explodes, right? As we said, right, basic physics and maths, you just pay attention, you work through your problems, you do your exercises, and I think you'll be fine, right? If you have the aptitude for these things, then you'll be fine, right? So I would say the most fundamental misconception that people seem to have is that somehow you need to be better or cleverer or more kind of intelligent than everybody else to do well in quantum technology. I mean, actually, it goes to like all kinds of other fields. Somehow people who work in AI are somehow more clever than everybody else. No, they're not. They're just basic statistics and probability theory. That's all it is, right? With some additional garnish on the top. The same with quantum technology. So I would say, yeah, just go ahead and do what you like to do and not be afraid of what other people say.
Yeah, and I'll add to that point. I'm pretty sure I made that statement like, "Oh, we don't actually understand what's going on in quantum," earlier, but I always put it as kind of like this joke, and to ease it, like if I'm going to say it to like a crowd of non-technical people, like I gave a talk to my university as a public speak earlier this semester. It was just kind of to be like, okay, we're going to talk about quantum, but chill. Like it's okay. I'll walk you through the things that might be a little foreign to you. We'll be all right. It's not, but I think the other misconception is if you do talk to people maybe that are not in the field, like it's not all quantum computing. Like it is the hype right now, you hear it everywhere, but there are a lot of other areas you can do. Like sure, I work in, quantum sensing in itself is also just super broad. Like you can say you work in quantum sensing, but what is that? It can be so many different things. So I think the misconception is that like you're only doing like a few things is false, If I wrote it out recently, it's like when I was at Sandia, I was working on 7 different projects, but because they were all dealt with quantum and I had that base, I could work on each of them. So you can do so many different things and go down so many different avenues in the quantum technology and information space that it's not just 1 or 2 things. It's not, quantum computing or, quantum sensing isn't one thing. It's a lot of things. And quantum computing isn't just one thing. It's a lot of things. So you actually do have a wide landscape to pique your interest in whatever it might be.
Yeah, these are great comments. Yeah, I hope the audience is particularly enjoying these, because I think they're very insightful. So we have one.
If I may add one brief comment on this. I mean,
yeah.
the fact that sort of somehow, I think people are I don't know, programmed to be afraid of quantum things, I think is partly like cultural in the way we teach students physics, I think, right? I mean, like from the very beginning that, oh, quantum mechanics is the theory of the extremely small things and tiny atoms and what happens inside atoms. And of course, we can't see atoms to the naked eye. And so it's very complicated and it's very mysterious. And there's this wave function that sort of flies around everywhere and so on. But if you think with like other areas of physics, that people somehow say, oh, classical physics or gravity or Newtonian physics is very obvious and very strange and so on, or very, very simple. It's not actually true, right? It's a question of just cultural experience, right? I mean, we are all told that the sun or the earth goes around the sun, right? And we know that to be true, and we've been taught that. It's in all the books and so on and so forth. How many of us have actually personally verified that fact? Or how would an individual go about verifying that fact? How evident is it to us that the earth goes around the sun and not the other way around? Is it any more accessible or less accessible than the behavior of an atom inside a molecule? So I think it's just people get into these mindsets, which is, I would say, largely cultural, that somehow makes quantum more mysterious than other parts of physics somehow. Which it's not, but it's just another part of physics based on experiments that people have done. So I think if people keep those things in mind, I think it probably will be less mysterious than it actually is.
Yeah, and I think I 100% agree with this. And it's actually one thing I'm trying to do. I teach some introduction, is kind of bring some quantum concepts into those classical things that we talk about with Newtonian physics all the time. We're not, a professor of mine, great mentor, he's like, we're not teaching artillerymen anymore, so we can stop talking about cannonballs. But you can actually get Newton's kinematics out from doing atom interferometry. Now, sure, I'm not gonna, their intro, they might not have the math background for me to walk them through the whole thing. But I can point out after showing them some kinematics where these two things in quantum mechanics that are just probabilities of being in a certain energy level actually relate directly to your acceleration. And it actually comes from just looking at an equation saying, oh, that's Newtonian kinematics. That pops out. So you can kind of sure, it might be somewhat foreign to think of what these probabilities are, but they're going to have time to learn that on their own and over the years. So you can kind of bring these concepts in earlier. So make it less scary. I think there's an issue with us waiting so long to actually start talking about them. So just kind of hopping on and agreeing with what Animesh said.
Yeah, these are great comments. Yeah. So I think with the last bit of our time here today, we have a couple questions from the audience. So the first one says, you mentioned some unsolved challenges that scientists are focused on, such as quantum states of light. What are some of the most unsolved problems you're anticipating within quantum sensing during the next 5 to 10 years? In your opinion, what would be the most difficult to solve?
Bill, if you want to start.
So I think for me, and what I've been working on recently is that you can have certain anomalies appear. So silicon carbide actually has a temperature anomaly where this coherence time, this thing we really like, when we set this quantum state, it stays in this state for a certain amount of time, and we can read it out very accurately. Well, normally when temperature increases, this just decreases. And that was intuitively what everyone thought. And we're like, okay, but recent work, and I say recent, it's about 10 years old now, saw that actually this coherence time started increasing at some nearing room temperature. And it was just like, okay, why does this certain anomaly happen? And it's actually, you have to dive into some nonlinear effects that are occurring. So I think some of the walls, at least on I'm a theory guy, so the theory side of me really finds interesting is what are these nonlinear effects that a lot of times, because of how complex it can be computationally or something, you kind of want to make some assumptions to help you out. breaking through that, getting, maybe with the help of AI to do some of these computations for us to make them faster, is learn what those nonlinear effects are doing and really start to understand the system better. And maybe we find a material that has this anomaly happen at room temperature, and then we're like, why are we looking at these two materials all the time when this one actually gives us the better efficiency when we want to make something for a room temperature application? And it comes from, this weird nonlinear effect we never even thought to think about. So for me as a theorist, it's looking at those weird non-idealities and anomalies that, in the next 5 years, as we learn more about them, can really actually kind of maybe put the reins back in the theorist's hand for a moment and start steering some experiments in a different way. I hope that made sense.
Right. So for me, I think the biggest challenge, the unsolved challenge specific to quantum states of light is the problem of loss. Right. So optical loss is inherent, right? And it's almost fundamental in the sense that, when light moves from one medium to another, there's a change of refractive index, whatever, and then you get scattering either forward, backward, and you lose some of the light, right? And the problem is if you then have, so for instance, if you have classical light, so coherent state coming out of a laser, you lose some of the light. What happens is you're left with the same state of light, just a bit weaker, right? So you had, I don't know, 1 billion photons, you lose a few percent. You still have a coherent state of light with just a few percent fewer photons, right? With quantum states, that is not the case. When you lose photons, the state of the light itself changes, right? And overcoming that it's a two-pronged problem, right? You obviously want low loss materials, so materials that have lower loss, but this is, I don't know, I'm not a material science expert, but I'm sure things can be improved because we know in the last 10, 15 years, things have improved a lot. Losses have gone down. I don't know how low they can go fundamentally. There must be some fundamental limit to how low losses can be made. So then the question, and this is the question then for the theory side, is how do you tackle these losses, right? How do you do quantum sensing in the presence of these losses, in overcoming these losses? And I think in the end, that's just my own personal opinion, I think we'll have to do something like error correction, right? Because you can think of loss as a form of error, right? That you send something and you lose a bit of the information and so on. So I think in the end, if we want like large scale or scalable quantum optical sensors, we'll have to deal with loss via error correction, right? But that's how loss in the end you can deal with. It's a form of error and you have to deal with. Not much work is done on this because again, people somehow have the notion that building a quantum sensor is easier than building a quantum computer, and we shouldn't have to worry about things like losses and error correction and so on. We've done a bit of work on this, but I think going ahead, this like tackling losses, whichever way, I think would be the big thing for quantum optics.
Yeah, and if you don't mind me adding on that, like I work in noise, so noise and loss go hand in hand. And that's one thing. Like the big thing with atom interferometers is that you can measure something very, very accurately. Like these inertial sensors measure local gravity to 14 decimal places. Well, 14 decimal places, if you have a small amount of loss, that's a huge effect. So you like just, okay, it's a quantum sensor, you know how to build it, there you go. It's like, well, the whole point of it is how accurate it is. These little losses, these error corrections you need have to be in there. They're super important. Otherwise, what you're getting out is just gibberish because it's now lost all that accuracy.
Yeah, to add on top of that, and this will get harder as the sensors get more and more sensitive, right? Because the more sensitive the sensor, the more susceptible it is to losses, right? So this problem is only going to get more and more acute instead of sort of going away, right?
Yeah, really great insights. Yeah. Our second question so far from the audience that we have here is, what about quantum sensors based on other charge carriers? How do they compare both advantageously and disadvantageously to optical quantum sensors?
Yeah, maybe Philip, you can go with this, but I'm not quite sure.
So I'm trying to make sure I understand the question. So like, a lot of the quantum sensor I work with have, some sort of optical side with them. So I'm not as familiar with the charge carrier side. So, advantageous to disadvantageous, a very, unexperienced way of looking at it is more on, I guess the system you're working with. On the the optical side is a lot of the quantum sensors that are doing it more optically. They're naturally sensitive to fields, and those fields can be very small. And so even making a small spectroscopic change, you can see giving some advantage where on the circuitry side of things, you have a little more to worry about. You can have these different types of noise in the circuitry that might not, from the charge carriers, that might not show up on the optical side. But then again, you have your own noise from the optical side that might not show up there. So my naive, unexperienced side with literally one half of this question is, I would say you kind of have to take it based off what your application is and what's going to be more advantageous and what's going to be more disadvantageous for you. Because if you have something that is building, that is looking at a lot of, current or something, maybe a charge carrier one isn't going to be as advantageous to you compared to an optical based sensor, or, vice versa. So that's my really, non-expert, answer to literally half of this question. So
yeah, I don't know if the person who asked the question is around. Maybe they can clarify what they mean by sensors based on other charge carriers. I don't quite understand the question. I don't know, is it possible to ask for a clarification from the person who asked the question? Like, is there an example they can give of what they mean by other charge carriers so that I can actually provide some sort of...
I don't see any clarification in the chat.
They've gone away.
Perhaps.
Maybe there's not just based on defects, they say. Well, I mean, there are quantum sense. I mean, atom interferometers, they're not based on defects, right? They're just based on atom.
they're based on atom clouds. So in that sense, it's more of just, it's the application space you're trying to get at. You also have things like, again, I worked on multiple projects like an optical centrifuge, which is doing spectroscopy in a very certain way. So it's more the application space. You can, atom interferometers, are trying to measure one thing, and they measure acceleration very well. Defect sensors don't really do that. They're, because you're an atom interferometer, you're allowing an atom cloud to fall, so it can measure those local gravitational things very accurately. A defect sensor is in a material, solid state, compact. It's not doing anything. So yeah, I guess my answer before is just, it's all about application space for your sensor that you're trying to use and where it's going to be useful.
Okay, no, I understand. Yeah, so I can see some sort of clarifications. Okay, so sort of plasmon-based sensors or exciton-based sensors. Yes, I think it's, yes, this again, I think is probably an important conceptual, let's say, aspect to keep in mind, right? Is that in sensing, you start not with the sensor, but with the object that you need sensed, right? So what do you want to measure or sense, right? Do you want to measure speed? Do you want to measure temperature? Do you want to measure wavelengths? Do you want to measure time? I mean, so each of these are like, there are different ways of measuring these things, right? So if you want to do, for instance, like spectroscopy of a molecule, right? So you want to know what molecule is there in my environment or whatever little sample I've got. You say, okay, I want to shine light on it in some way. And then there are a huge array of ways of improving that, right? So you can say, okay, I can put my sample in a cavity, I can put my sample inside another sort of matrix to improve the interaction with light and so on and so forth. So I think it always starts with what is it that you want to sense and how do you want to improve your sensing, right? And the other question or the other aspect that is very crucial in this, and I think again gets often overlooked, is what is the best existing classical sensor for the same thing, right? Because very often people have this idea, and I especially get this from talking to sort of people in industry and so on. They somehow think that quantum is a magical solution to all their problems, right? It's not. It probably creates as many problems as it solves, right? So you really have to be absolutely sure that your present way of measuring whatever it is you're interested in measuring is going to be bettered by using a different quantum technique, right? So yes, if you want to have some molecule which is not, say, sensitive to how much heat it gets and so on, so you can put it inside a plasmon-based sensor, because that's how they basically increase the interaction of the light and the molecule, but obviously that generates more heat because they focus the light very strongly. And then if you're interested in a biosensitive molecule, that's not very good because that's then going to damage your biological thing and so on and so forth, right? So I think it at some level, then at this level, it becomes extremely context dependent, and then it gets more and more technical, and it gets harder and harder to give sort of generic answers, which is well often, and yeah, I think I'll stop with that. I hope it was to some extent of help to the one who asked the question.
Great. Yeah, I think that is all we've got at the moment. We're also at the top of the hour, more or less. So I think that's all we will go through today. So thank you again to our panelists and our audience for joining us for this conversation. Please do check out the rest of the Quantum Series webinar episodes. They are monthly throughout 2025. We have one more in December. So it's in celebration of the International Year of Quantum Science and Technology. So once 2025 is over, so is the webinar series. But yeah, thanks again to everybody for joining us, and check out the recording on YouTube. And thank you again.